So I'm going to talk today about big data analytics and how you get business value out of it with, in particular, an industrial flavor to it. So first of all, what is this all about? At a very high level, the key thing this is about transforming the way that the physical world works. So if you look at industries where data and IT are already a core fundamental part of the value proposition generated. This is things like in financial services and telecom, where the business is basically about how you move numbers around better, how you manipulate numbers in better and more creative and useful ways. Those industries improve at levels gated by IT to a large extent. And so you see them spending a lot of money on IT. So in those industries, financial services and telecoms, you see numbers in the 5 to 7% range in terms of the fraction of revenue they spend on IT, right? And that makes sense for them. But if you go and look at very physical industries like mining and oil and gas, they spend in targeted ways on IT sometimes, but on the whole, those industries spend about 1% or so, maybe a little bit more, maybe 1.5% on IT. And that's because those industries still are fundamentally about very physical things that aren't yet controlled by IT and analytics. But the really important thing, this is what got me really excited about this area when I first started getting into it, is that if you look at the trends, if you look at the time derivative, some of these numbers, you're seeing these very heavy physical industries ramping up their spending dramatically on IT and analytics. Okay, and they're coming off a small base, but it's a very noticeable trend, and that's because more and more, all these devices that they use, the heavy equipment, are connected. People are applying analytics to it, and you're able to see some of the benefits you see in more IT-heavy industries in productivity and performance in these industries. And that's really, really transformative. I mean, that could change the world in ways that we think it's even hard to comprehend right now. And the contention here is that big data plus physics, and not just big data in the traditional sense that it's usually talked about here in Silicon Valley and really all over the world, but big data supplemented by domain knowledge and understanding and physics and engineering is the big enabler that's going to gate this or make it happen much more quickly. So just a minute here on the business value associated with this. So there's all kind of numbers that you can see thrown around on this, but pretty much the common characteristic of these numbers is that they're very, very large. So for example, you have some numbers here in the aviation industry. If you could just get a 1% improvement in fuel savings over 15 years, that's going to give you about $30 billion in net bottom line impact. The power production industry, 1% fuel savings cost there is about $66 billion over 15 years. And there's other numbers. I've seen other studies, one study done by a mining company, for example, that showed if they put together the kind of IoT / data and analytics systems that we're going to talk about here in a few minutes across their entire enterprise, their $30 billion in revenue that they have, that as the level of size of their company would generate about $3 billion additional to the bottom line every year. So the only common point across all these numbers is they're all very, very huge for a pretty small impact. The key thing is, can you make it happen? And there's a lot of things in the way we'll talk about, but there's a huge amount of opportunity. So just to kind of make it real before going into the analytics and how we do this, I want to give an example from a wind farm. So in GE, we have a pretty substantial wind turbine business. And the way a wind turbine works, you have to look at several levels. A wind farm works, you have to look at several levels of abstraction. So there's the machine level, right? That's what's generating most of the data here right now, most of the sensor data at least. Now, a given single wind turbine might be generating about 100 tags, as we call them. That's 100 sensor variables, maybe every 40 milliseconds or so, okay? And so that's 6,000 or so every minute, and then depending on the size of the wind farm and some other factors, it's in the order of millions of sensor data points coming out on a minute sort of time scale. Now that's just the sensor data. You combine that with all of the other operational data, the asset management data, the production data, and then things like the physical environment and site data, the weather. And not just weather in terms of is it raining or what the wind patterns are, but the temperature, humidity, dust levels, other kinds of particulates can be very influential. Even things like bugs, believe it or not, the insect population in the area can have a big effect on a windmill operation sometimes. So when you're looking at the turbine level itself, you're looking at things like how should I point the turbine, what changes should I make to the gearbox, and many other factors to optimize the operation of that turbine itself. But then you go to the level of the person who's operating an actual wind farm. They've got to consider interactions between the turbines. Because you have a turbine facing in one direction with the wind, that creates a wake and other complicated fluid dynamic effects around it that affects the other turbines. So you want to optimize this in a way using all of the turbines. That leads to some very complicated mathematical optimization calculations. And then you have to be gating that based on predicted demand. So now you're looking at your customers. What is the demand going to be? What's the upcoming weather in the future? Will I be able to meet that demand? So there's enormous amounts of data analytics and processing, enormous amounts of data, and a lot of unsolved problems to make this work better. Now, the critical ingredients to get to what we're talking about, those kind of numbers that I showed you before, there's 4 things that we've identified as really critical to this. One is software-defined machines. I know there's been some discussion about that here already. The other is the connectivity element, the Internet of Things kind of element here. But the part I want to focus on in this presentation today are our numbers 3 and 4 here, which really are what we call the industrial data science part of it. And that's the combination of the deep domain capability, the physics and engineering-based models and the operator expertise models, combined with the traditional big data analytics. That's pretty new. So first, just on the software-defined machines, this is a topic of a lot of discussion. I won't belabor it here. But we've all seen this happen in the consumer space. Looking at the crowd here, most of you will remember when phones were not software-defined, that you had hard-wired buttons and you couldn't really change the functionality of your phone over time. You have to buy a new one. Some young people today aren't even aware that used to be the case. And that's really transformed the consumer space. It's transformed the way companies relate to their customers. It's transformed the kind of things you can do, and so on. We see the same thing happening in the industrial space, where we want to make our machines, whether it's an aircraft engine, a locomotive, components in a city, the lighting and other kind of infrastructure in the city. We want to see those things be able to be dramatically changeable at the edge. That gives us. We need to have that to have an ability to change the physical infrastructure in a way, again, that software and analytics can drive a lot of business value. So the device behavior has to be adaptable. The second part on the IoT or connectivity side, kind of stepping back as an example again, we all kind of remember what happened when the internet first came out. Again, looking at the people in this room, a lot of you probably can recall personally, some of the earlier days of the internet. And, 1 billion people became connected over time, right? And the kinds of things in the early days of the internet, and we're in the early days of an industrial internet right now, the very early days. In the early days of the commercial internet, people made a lot of wild predictions about what the internet was going to do for us, what was going to happen. And a lot of them, you go back and look at those magazine articles now, they look kind of quaint and naive. And the way things turned out was as or more dramatic even than a lot of people thought, but quite different. People didn't really anticipate way back then how social media would emerge and how that would affect how people interact and so forth. They didn't really anticipate all the impact of mass virtualization and cloud and so forth. So we kind of see in the industrial internet, when you connect 50 billion machines now, a lot more, we have our baseline assumptions about what this means and how we're going to make overall industrial systems and physical infrastructure work better. But we all kind of, in a humble way, think we probably have no idea what's really going to happen and what the big killer apps are really going to be and how it's going to change the world. So we're very, very excited about this. Now I want to segue into the industrial data science side. So one of the things that I was tasked with in GE is to try to create a modern industrial data science capability that can scale and have impact at our company level, right? And so there's a lot of misunderstanding about what data science is. Some people want to treat it like software. They want to say, well, here's the requirements. I need a model that'll predict failure of this component within 10%. When can you deliver that, and how much is it going to cost? And the thing is, with data science, there really is an element of science to it. In other words, you can't really. It might be the case that given the data you have, it's literally impossible to deliver that kind of a thing. You can't just spec it out. And so there really is a necessary exploration phase in front of any kind of data science engagement where you need people to be able to look at the data and assess even what might be possible with it. And so it's not it's not quite as bad as this cartoon suggests, it being a miracle needed to make stuff happen, but we need to develop the right ways to enable businesses to plan for data science-based capabilities, but based on the reality that data science is a different beast than either other traditional kinds of physical science or from software. So we break data science into 3 major components here. The first one is the physics and engineering-based models. Again, a lot of people used to the traditional kind of big data and machine learning don't really think about this, but this is what we in GE and I think our industrial competitors have relied mostly on for the last number of years. So this says instead of just taking a bunch of data in and running machine learning or doing different kind of statistics on it and so forth, if you want to know when a component in this aircraft engine is going to fail, you model the material physics of that piece of material. You say, well, if it's at this temperature, that's going to lead to certain kinds of grain boundary migration and certain kinds of crack propagation and all that. You make individual components for each, individual models for each component in that piece of equipment. Now that's great because you don't need a whole lot of data. You need a little data to fit the models, but the real information is coming from the brains of the engineers and physicists working on this. It's very powerful and they can be pretty accurate. The killer on these, what makes them really bad, is they're very complicated. They require deep, deep domain expertise. And so if you suddenly change the design of the engine, you change a material or a coating, you got to go start from scratch again and develop that again. And that's very time-consuming and costly. And then if you want to go to offer more value for your customers, to go beyond the equipment that you make and that you therefore know in depth the physics and engineering of, you're kind of lost because you don't have that knowledge for those. So it's great where it applies, but it applies in a limited set of areas. The second kind is the empirical or heuristic rules and insights. So this is the kind of stuff that operators of heavy equipment have. So an oil company, for example, an oil and gas company, or an airline that operates the airlines. These tend to, and this, by the way, is the kind of analytics that predominates in most industrial operations today. And this is things like, well, if this temperature is rising this way, well, this pressure is over this threshold, that means the equipment's in a bad state, you better have someone go look at it. So it's that kind of stuff. Now, those are really good because, number one, they encapsulate the knowledge of your workforce. That people who are there that developed this expertise over the years, when they leave, you don't lose their knowledge because their knowledge can be contained in these rule sets quite well. And also because they're rules that make sense to the operators have very little resistance to using them. When you try to do physics-based models or some of these big data-driven models and neural networks, a lot of the operators just push that away. They say, I don't believe that bunk. It doesn't make sense to me, I'm not going to use it. Whereas these rules make a lot of sense to them, so they use them. The third technique is the data-driven technique, and this is all the machine learning, advanced visualization, advanced stats, optimization, and so forth. And again, it's the kind that people often think of exclusively when they think of analytics or data science.